everybody, today we're going to be looking at 5.1, where we're going to be looking at both exponential and logarithms. Logarithm is the new kind of topic for this quarter and for this year for Math 3 and everything. So that's kind of the focus of what we're going to be going through today. And the big question is then where do logs come from? What do they represent? And how do we use them? So starting out with this starter, I want to look at just a basic two-step equation. How do I solve this? Okay. And most people are pretty okay with this. Most people go, okay, well, I'm going to do subtract 5. But the question I want to ask you is why? Why are you subtracting 5? Why are you not dividing 5? Why are you not multiplying 5? Why are you not dealing with that 2 first? Why are you subtracting 5? And the reason is because really what's happening here is we're trying to do the inverse of plus 5, right? Minus 5 is the opposite or the inverse of addition. Okay, so then I get 2x equals 8. Okay, and I have multiplication happening here. The inverse or the opposite of multiplication is, of course, division. Okay, and then I get 4. So in math, we like to have these inverses where addition is the inverse of subtraction. Multiplication is the inverse of division. Squaring something, the inverse is taking the square root. Okay, so on and so forth. Sine. Remember we did last quarter. The inverse of sine was just that sine inverse. Okay, so the last thing we need to figure out what the inverse of is when I have an exponential where x is in the exponent. Okay, so not like this, not where I have x squared or x cubed or x to the fourth, right? Because even x cubed then would be cube root of x. Okay, now unfortunately we can't just do the cube root of x. Okay, that doesn't exist, or it's not something we use. What instead we use is logs. Okay, and in this case, I would use log base 2. 2 and 2. So these two functions are inverses of each other. Okay, so what does that mean graphically? Well, let's start off by looking at just exponentials for a second. Okay, so we're going to ignore this right side for a second. Okay, just ignore that for 1 second. We're going to look at this left side. So an exponential graph should look very familiar to you. You've seen of them a lot lately in the news. You've seen them a lot lately with dealing with coronavirus, with dealing with the GameStop stock. You see it in nature a lot when you deal with bacteria growth or virus growth, even population growth follow an exponential curve. So let's head over to Desmos real quick and let's look at what those exponential curves look like. So let's start off with just 2 to the x. Okay, let's zoom out a little bit so I can see what's going on a little bit better. Okay, so I can see as I go right, this thing is going up very, 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 very quickly, even faster than x squared. Let's look at x squared for a second. Okay, so if I zoom out way, way a lot, right? Okay, there is a portion where it's going up a little slower, but then it starts going up much quicker than even x squared if I go way, way, way up here. Okay, so even dealing with 10, I'm in the hundreds. Okay, whereas 2 to the x dealing with 10 would be much, much bigger. So here's 2, right? Or 10, sorry. It's around 100, but here it's 10 is way, way up here. Let me find it. Like I'm not even there, and I'm already in the 500s. Probably in the close to the thousands. Yep. So probably I think it's 1028. Okay, should be right around where 10 is, or 1024. Okay, so we see that, again, we have this curve that goes up very, very rapidly. So let's get rid of this, and let's look at some other ones just real quick. So like, for example, I have 3 to the x, okay, 4 to the x. Okay, and as I go up in number, they all go up much faster. But if you notice, on every single one of these, my x-intercept, or my y-intercept, sorry, is 0, 1. On every single one of these, I go through 0, 1 every single time. If I look over to the left too, as I go left, I'm getting very, very close to 0. Now here it does say I actually hit 0, but this is a rounding error in the program. I never quite actually get to 0. See how it's like 0.001? This would really be like 0.0001, maybe another 0 as you go left. Okay, so while it does say it goes to 0, it never quite gets there. And I can zoom in really close and kind of see that. Okay, where it's not quite there, especially on this red curve, a little easier to see. Okay, and again, I can keep going in for those blue and green ones, and eventually I would find that it's not quite at 0. It's close, but it's not quite there. Okay, even for these ones now, I can see it's not quite at 0. Okay, so let me reset this just to get back to the normal. Okay, so again, to the x. So again, we notice that we have it going through 0, 1 every time. All the x's seem to work. Y's domain really is anything bigger than 0. It never quite gets to 0. We have a horizontal asymptote there, is what we're going to talk about later. Okay, but that's the idea here. Now, if I took this and I flipped it down, okay, because that's how I find inverses. So I'm going to need some points. Okay, now I want to use positive points here just because it's going to make my life a little easier. Okay, and there's those points on this graph. Okay, I'm going to zoom out. I can get that 32 way up there. Okay, but as you can see, these things go up very, very quickly. So if I took this and I inverted it, then remember, an inverse flips over the y equals x. So it's going to take that, it's going to flip it down over y equals x. So again, what we're going to do is we're going to do log base 2. Actually, I need to do... So on Desmos, you go to functions, miscellaneous, and then this log base a. And then it'll let you put that 2 down there of x. Okay. Which I can see flips over kind of nicely, right? And then I can make a table with that, right? And plug in these numbers. So 1. You'll notice here there's a bunch of undefineds. Okay, that's going to be important in a second. We have 1 and then 2, 4, 8, 16, 32. Okay, and again, you can see again with inverses, we can change the x's and y's, and we get that new graph. So that's where log comes from. Log is this inverse function. Okay, it flips very nicely. Because we had a horizontal asymptote on exponentials, we have a vertical asymptote on these ones. Okay, so going back, going back here. So domain for all exponentials is always going to be all real numbers. Range for the parent function for every parent function, whether it's 2 to the x, 3 to the x, because you notice we have a b here, 5 to the x, 6 to the x, 7 to the x, doesn't matter. Every parent function is always going to have a range of 0 to infinity. We'll move these around later where that changes, but for right now, that's true. We have a horizontal asymptote for every parent function at x equals 0, or y equals 0, sorry. We have an intercept always at 0, 1. Okay, and don't worry about the end behavior. We don't need that. Now, there's 2 points here that I always know. I always know 0, 1, and this is always true. And then I have 1 and whatever my b value was. So if it's 2, it's 1, 2. If it's 3, it's 1, 3. If it's 5, it's 1, 5. If it's a million, it's 1, a million. Okay. The only rules and the only exceptions are b cannot be 0 and it cannot equal 1. Okay. The reason for that is anything to the first power, or first power to anything, I should say, is 1. Okay, because 1 times 1 always is 1. 0 kind of does the same thing. Okay, it acts really funky at 0. You can see here, but because of this, we cannot have 1. We cannot have 0. -1 also behaves strangely, and doesn't work nicely for us as well. Okay, so x or b cannot be 1. Cannot be 0, cannot be -1. Okay, so that being said, this is my parent function here. Flipping that down, if I had 0, 1, I'm just going to swap the x's and y and get 1, 0. If I had 1b, I'm going to get b1. Okay, and b is coming from the base. So let's graph some of these. Starting out, always start with the asymptote. Okay, my asymptote is right here. Okay, I know based on what we saw earlier, if I plug in 0 for x, I'm always going to get 1. If I plug in 1, 2 to the first power is 2. If I plug in 2, 2 squared is 4. If I plug in 3, 2 cubed is 8. 2 to the 4th, 16. 5, 32, so on and so forth. Okay, it's really these first 2 numbers that we're going to plot. So we're always going to do 0 and 1, and I get a nice curve that looks like this. Okay, again, it's going to get very, very close to this asymptote on the left. Now I've never quite hit it, and then on the right, it goes up very, very quickly. For logs, that just flips over. So since I had a horizontal asymptote, for logs, I'm going to have a vertical asymptote. Okay, instead of it 0, 1. So again, taking those x's and y's and just swapping them. I'm going to get 1, 0, 2, 1, 4, 2, 8, 3, 16, 4, 32, 5. Again, the only 2 I really need to plot are 1, 0 and 2, 1. And it looks something like this. Okay, again, it's going to get very close to this asymptote, but never quite hit it. So these are my 2 big parent functions we're going to use, okay, for 2. If I had 3, the only difference is it would go up to 3 instead. If I had 4, it would go to 4. If I had 5, it would go to 5. But it always goes through 0, 1. Always. Okay, so the other number that pops up a lot in math is E. So E is one of those numbers that I know it looks like a letter, but it's really a number. E is approximately 2.71928 1928459045 2, I think it's 7. 27 or 23. Okay. You don't need to memorize that. E is about 2.7. Okay. E is one of those numbers that pops up in math a lot, especially in physics and engineering. So if you're going into a physics or engineering field or a math heavy field, you're going to use E a lot. If you're not, honestly, you'll probably never see it again. Okay. But it's a number that pops up in nature a lot. It's a number that pops up just kind of in engineering a lot. So it's a number that's good to know because it's so special. Especially with dealing with exponentials, it gets its own version of log that we call ln. If I look on my calculator, I've got log right here. I've got ln right here. Okay, and we won't be using the calculator much today. We'll look at it more next time. But if I notice, it still goes through 0, 1. This one still goes through 1, 0. Okay, but 1 is at about 2.7. Okay, and 2.7, because 1 would be right here, is at 1. So let me write that more better. 1, 2.7. There we go. Okay. And that's the real big difference on this one, is just where that 1 value is. Just like with 3, just like with 4, just like with 5. Okay, so let's look at graphing any of these, because that's the important part here. Okay. So my transformations, you're going to have 2, or really kind of 3, but mainly 2 big transformations you're going to have to deal with: flips and shifts. If you have a negative out front, this is going to be a flip over x. Over x, not 4. Okay, and then any number not with x. If you notice, this is down here. If it was with x, it would look like this. Okay, see, it's not really up there with the x, it's down. So if it's not with x, those are going to be shifts up and down. We'll look at one in a second where it's not a shift up or down. So in this case, it's going to be a shift up because it's positive. Okay, now that not only shifts that 0, 1 point, and not only flips that 0, 1 point, but it also shifts and flips the asymptotes. It really just shifts the asymptotes. So if the whole graph shifted up by 1, if my asymptote was originally at 0, well, now it's moved up by 4. So my asymptote now is at y equals 4. Okay, I started here, and then I moved up by 4. Okay, now the point on the graph is a little trickier. So my point that I'm always going to do is always going to be 0, 1. So I started at 0, 1, and my graph looks something like this. Okay, I need to do this flip first. So it's going to flip over x, so it's now going to be down here. Okay, and then I'm going to move up by 4. So I started at 0, 1. I moved down by 4, flipped over. So now I'm at 0, negative 1. And now I'm going to move up by 4. So plus 1, negative 1 plus 4. I'm going to go 1, 2, 3, 4. And I'm going to be at 0, 3. Okay, so let me clean this up a little bit, just because I don't really need all those extra numbers. Okay, so I started here, I flipped over, and then I moved up by 4, 1, 2, 3, 4. Now I am at 0, 3. Okay, and again, since I flipped down or flipped over, it's going to go down instead of up. So my graph will look something like this. Doing one more of these. I'm going to do it on the same slide. Okay, I'm just going to change my function a little bit. So I'm going to say, let's say 2 to the x plus 2. Let's say 3 actually. So we have different numbers. Minus 1. Okay. This 2 is never going to really affect anything. That just affects your second point, how steep this thing goes up or down. It's this 3 and the negative 1 that are going to do things. So the negative 1 is not with x, so it's going to go up or down. So it's going to go down by 1. This 3 is up here with x. So since it's up with x, it's going to go left or right. In this case, it's going to go left. Remember, anything that is inside with x always does the opposite of what makes sense. So since it's up there with x, instead of going right, which makes sense, it's going to go left. Okay, which means my asymptote is going to be at y equals negative 1 because I went down by 1. So my asymptote is down here at negative 1. Okay, I started at 0, 1. I went down 1 and then left 3. So now my point that I'm going to be using is at -3, 0. And then it just comes up and goes up like this. Okay, logs, same idea, except the point we're going to use is going to be 1, 0, and I've got vertical asymptotes. Okay, so again, same idea. Inside with x tells me I'm going left 7. Again, it's the opposite of what makes sense. And then outside, down 3. Okay, now again, on logs, I have a vertical asymptote, not a horizontal, vertical. So it's the shift lefts and rights that are going to change this. So I'm going to go left 7. So I'm all the way over here. I was at 0, now I'm at 7. For my point, the point I'm always going to use is this 1, 0 point because it's always the same. Okay, 1, 0, I'm going left 7, so I'm over here at -6, and then down 3. 1, 2, 3. Doesn't really matter if you go left or right or up or down first. Flips do matter. Flips do need to happen first. I don't have a flip here, though. Okay, so then it's going to go this way up to it and then start going right. So it'll look something like this. Again, we're just looking for sketches today, nothing fancy. Okay. Last thing we need to look at, domain. Because if I look back at logs, and let's go back to that graph that we had earlier. If I have log base 2 of x, again, we have that vertical asymptote at 0, meaning nothing can exist at 0. Nothing can exist in the negatives. Okay, I could do any negative here. It will always give me undefined or no solution. So because of that, I have to have x or what's inside the log greater than 0. Okay, it can't even be equal to 0. It has to be strictly greater than. So that being said, I'm going to change this one. Hold up. I want to look at the inside here. That inside needs to be greater than 0. Doesn't matter what's outside. Doesn't matter what the base is. We have base 5 here. It doesn't matter. Okay, it's what's inside that needs to be greater than 0. This is the important part. So I'm going to set that greater than 0. -1, -1, 4x greater than -1. Divide by 4, divide by 4. X needs to be greater than, not equal to, sorry. Greater than -1 over 4. Okay, if it's not, then I have something that is 0 or less, which means it cannot exist. Okay, let's look at one more. Let's do log, or let's do ln, because again, it doesn't really matter. Let's do 5 ln of 3x plus 5 plus 106,502. Okay, again, this doesn't matter. This doesn't matter. It's what's inside that matters. So 3x plus 5 needs to be greater than 0. -5 minus 5. 3x needs to be greater than -5, which means x needs to be greater than -5 over 3 because I divided both sides by 3. Okay, so my domain restrictions. So if the question asks for domain restrictions, this is what you do. Okay, now, if you are a regular student or a virtual student, you are good to stop the video at this point. If you're an honor student, please keep watching because I do want to show you one more trick. So notice on this one, we're going to have something that's kind of funky that is happening. So I'm going to do -5 minus 5 still. Oops, greater than. Okay, now, whenever you divide by a negative number, you have to flip the sign. So instead of x being greater than, it needs to be less than 5 over 3. So that's just one more thing. Just watch for that. If you ever have a negative that you're multiplying by or dividing by, you have to flip the sign. Okay, that is it for this lesson. Please let me know if you have any questions, and I'll see you guys next time.